Hello people. Today we are going to talk about infinite series, which is one of the topics in calculus. So, those of you who are planning to take calculus 2 or are currently studying beginners calculus, differential calculus, so this video is going to be helpful for you because we are going to talk about infinite series. I'll introduce you what is it and what do we do with it, and talk about some terms which are very important for understanding of the entire concept. And then I will have a couple of examples as well for you to understand the concepts better. So let's see how it goes. So feel free to join and ask any questions, and yeah, I'll try to answer all of your questions. So let's go for it. So let me share my screen. And actually, I'm going to share the entire screen. And then I need to open up this PowerPoint. Basically, also need to set up my phone because then I'll be able to see your comments. So just give me a quick second. I need to just change the account into my, one second. Sorry, I forgot to do that first. um, I'm sorry, that's not the one.
If you want to get
Okay, here we are. All right. Right, so I'll be able to read your people comments on my phone, so that would be good. All right, so let's get started with series convergence. So let's first talk about what is an infinite series. One second. Let me just connect my marker. Oh, sorry. My bad. Yeah, so what is a series basically? So, specifically, what is an infinite series? So just to give you an example of sum, the conventional sum term we hear in mathematics, we all are familiar with it. So when I say sum of two numbers, 1 plus 2, makes perfect sense. We can find it equals to 3. 1 plus 2 plus 2, 3 plus 2 equals to 5. Again, a finite expression, finite sum makes sense. We can add finitely many numbers. But what happens if I do, okay, 1 plus 2 plus 3 plus 4 plus 5 and so on? So I never stop. I keep adding numbers and I never stop. So the question is this making sense? Is the end sum a well defined finite number, or is it going to be not defined or infinite? Can we make sense of it? So that's the fundamental difference between a finite series and infinite series, a finite sum and an infinite sum. We all understand the meaning of finitely many terms getting added up, but we fail to understand or interpret what happens when the number of terms in an expression is infinite. That's why we have this whole topic infinite series. So, in short, any infinite series always look like this. So some term a naught plus a1 plus a2 and so on. So it keeps on going. And then we have a condensed form to write this kind of expression. So we use this notation sigma, and then we denote the general term by an. So n is the running index and it goes from 0 to infinity. So that's a convenient way of defining infinite series. This form is known as expanded form, and this form is known as closed form or compact form. So most of the questions which you will find will be given to you in compact form, but sometimes it's good idea to expand few terms just to get a better understanding of how do the terms of the series look like. So let's go ahead. So I hope you understand the meaning of infinite series. Now, the big question is convergence. So the thing which I just talked about, whether that infinite sum makes sense or not. So if it makes sense, means if it is a well-defined number, then we say the series is convergent, otherwise divergent. That means if I am able to say something like this, that this ends up into something finite, that means the series an is a convergent series because it converges to one value, the sum converges to one value. But if this quantity is either infinite or not defined, like sometimes it's not necessarily it goes to infinity, sometimes we are not even able to make sense of it, that where it is going or will it ever reach somewhere or not. In that case we say this series is divergent. So knowing whether a given series is convergent or divergent is the first important question we need to answer. Once we know a series is convergent, there are a lot of things to do with it, like a whole branch of mathematics develops from there. And once you know series is divergent, there are a lot of things you can do with this as well. But knowing whether a series is convergent or divergent is the first thing we want to do. And that's what we tend to learn, how to know whether a series is convergent or divergent, right? So now you understand the meaning of convergence. So now we are trying to find out how do we know that a series is convergent or not. So there are many ways to do that, or in other words, more precisely, I would say there are many tests of determining convergence, many tests, multiple tests. So some of them are general in the sense they are applicable to any series type, and most of them are very specific series kind. Like you have to recognize, okay, it's a particular type of series, so I can use this test, or it's a different series, I can use this test. And sometimes one test fails, you have to use another test. So it's a lot of I would say effort. It takes a lot of effort in identifying whether a series is convergent or not. But if you do it structurally and systematically, like you have your all fundamentals clear, you have a hierarchy of doing that, so you're not going to mess up with this. Because most of the times I have seen students getting struggle with this topic. They feel, okay, I know this test, but how do I know which question is made for which particular test, or where to use what? So I'm here to help you on that. Just to streamline this for you briefly, how do you know which test to be used where? So I'm going to give you a bunch of tests and give you an idea about their mapping with the specific type of questions. So the very first test we can think about in this topic is nth term divergence test. So it's clear from the name that it is a divergence test. So that means when we use this test, our final answer can be the given series is divergent, but our final answer can never be the given series is convergent. So this test never imply convergence. This test will imply divergence, or it will not imply anything, right? So it can never lead to convergence. So that's why it's known as an term divergence test. Now, what is it? So we have been given this series summation n is 0 to infinity, and it's not necessarily all the time n starts from 0. N can also start from 1 to -5 or wherever. And we'll talk about it, that it doesn't really matter wherever n starts from, because the index the a finite translation of the index does not change the convergence or the divergence. So for the time being, just assume n starts from 0 to infinity, because even if it is not 0, we can always bring it down to 0. So that's the given series. So the test is, you take this an and then you take limit n goes to infinity. That's a prerequisite for this topic. If you're not aware of it, I'm telling you now. Knowing how to compute limits, specifically limits at infinity, is the one important thing which you should know before you pursue the study of this topic. If you're not good at it, go back, study L'Hopital's rules, study how to compute limits at infinity, because every single question is going to involve computation of one or other form of limit. So you have to be really good at it. Otherwise, no. So go back, study limits at infinity, and then come back again. So limit n goes to infinity an. You compute this limit. And now, if it turns out to be non-zero, there is a if here. It's a condition. If this limit is non-zero, then we say this series is divergent. Otherwise, now what's the other possibility? So for any real number, there are two possibilities. Something is non-zero, something is zero, right? So even if the limit does not exist, it falls to the other category, zero category. It goes to this category. So the only thing when it is non-zero, I should actually write finite here. 1 second. Sorry, let's not go there. Let's stick to non-zero and zero, and then we will talk about later about being finite and infinite. If something is non-zero, the limit is non-zero, anything other than zero, it's divergent. If it is zero, then this series is, no, you cannot write it as convergent. Actually, we will be writing may or may not converge. In other words, may or may not diverge. Because a series could be one of the things. It could be convergent, it could be divergent. There has to be one unique answer. So if it is not divergent, then we cannot say definitely it's convergent or not. We cannot say it's divergent as well or not divergent. In other words, if limit is zero, you cannot imply anything from this test. The only thing you can imply is the series may be convergent, may be divergent. So in this case, the question will continue and you will have to use some another test, right? So you can't just leave your answer there. You have to use some other test. So we have a bunch of tests coming up. So you have to choose, okay, which one is applicable and use that, and boom, you get the answer. But things become really easy if you have this particular, I would say, limit in front of you. Like if this turns out to be non-zero, so you end up getting lucky. Okay, this is non-zero. I just know the answer now that this is divergent. So I'm going to give you some examples for nth term test now. So say you have this series summation 2n over n plus 2. Now an is 2n over n plus 2. So when you take limit n goes to infinity 2n over n plus 2, so now you can see it's infinity over infinity. It is indeterminate type of limit, which is the very common type of limit form, especially when you're computing limits at infinity. So since this is infinity over infinity, so we can use L'Hopital's rule. The L'Hopital's rule tells you you take the derivative of the numerator, you take the derivative of the denominator separately, and then compute the limit again. Since this turns out to be 2, a constant limit, and this constant is non-zero, so yes, we are lucky here. The limit is non-zero. You can say thus by nth term divergence test or simply nth term test, the given series diverges. So the question ends there. You got the answer. Now, I'm not saying this series cannot be proved divergent using any other test, but if it clicks to you that, okay, this can be done using nth term test, so do it. So that's why I always teach my students, whenever you're trying to do series, the first test you have to think about is nth term test. Apply it regardless of what type of series is it, right? It's a universal test applicable to all type of series. Just use it. If it is non-zero, you're done. If it is zero, you're not done. So now I'll give you an example where it is zero. So say you have this series 1 over n, very famous series in mathematics known as harmonic series. A lot of applications, a lot of usages in physics and simple harmonic motion systems. It's a lot of things associated with it. Anyways, coming back to this. So let's apply nth term test. So an is 1 over n. What is limit n going to infinity of 1 over n? So this is actually equals to 0, right? It's very easy to see this limit is equals to 0. Since this is equals to 0, so See, the nth term test told you if the limit is 0, then you can't conclude anything. So we cannot say anything. So we can only make this statement at this point of time that given series may or may not converge. So that means we need more tests to answer this question. So that's why I'm going to introduce another test now. This test is known as P-series test. Now, unlike nth term test, this test is not a general test. This is not applicable to all the questions. This is only applicable to a particular kind of series. You only have to recognize, and this one is the easiest one of all to recognize. It's P-series. So whenever you have any an of this kind, 1 over n to the power p. So p is any power, right? For example, you have 1 over n square, 1 over n, 1 over n raised to power 5 over 3, 1 over n to the power 7. So all of these are P series. So the moment you recognize these, you can use the P series test there. So even if it is 2 over n cube, it is still a P series. The only thing you can do with this 2 is you can take this outside the summation and write the remaining series like this. So that's another test, another general characteristic of the series which you can use. That if you're able to recognize a series and there's some additional multiple sitting over there, you can just pull this out of the summation because this is something which is free from n. So you can pull this out from the summation, right? So this one is a P series. And multiplication with a constant multiple does not change the convergence or divergence of a series. So whatever will be your answer for this, the same applies to this one. So very easy to play with the constant multiples. Anyways, come back to this. So whenever you have summation 1 over n to the power p as your P series, so what's the test? So the test is this series, okay, n is 0 to infinity. Again, I'm not writing specifically 0 to infinity because even if it is n is equal to 1 to infinity, the same test is still applicable. But just to keep it complete, I'm writing n equals to 0 to infinity. So this series is convergent if p is greater than 1 and divergent. Actually, here I should be writing n equals to 1 because 1 over 0 otherwise will be not defined. So this particular case, we have to have n equals to 1, right? Okay, and divergent if p is less than equals to 1. So that's the test, P series test, that the power p magnitude decides whether the series is convergent or divergent. Greater than 1, convergent, less than or equals to 1, divergent. Easy to remember. So now you can answer for all of these which I've written here. You see this one is going to be convergent because the power here is greater than 1. This one, the harmonic series, is divergent because the power is equals to 1. Equals to 1, it diverges. This number, the power is 5 over 3. It is again convergent because 5 over 3 is something greater than 1. This one is again convergent. I'm writing in short for convergent CGT. And this one is definitely again convergent. So it's very easy to use this test and it's always going to give you an answer. It never fails. It's never inconclusive. So, and these are the most commonly type occurring of series. They are very frequently occurring in these questions. And once you spot them, you get the answer immediately. So P series test. So now you can go back to this question. So this harmonic series was the series which was given to us. When you used nth term test, you were not able to conclude anything. But by P series test, you can say this series diverges or is divergent, however you want to write it, right? So it is quite possible that in one single question, you might have to make use of multiple tests. If one fails, you use another. But yeah, if one gives you the answer, then there's no point of using multiple tests. And that's what we want to learn here. We don't want to waste time on just trying random tests. We want to know the exact hierarchy. Okay, which test should be used first, and then there is an order. So here we have this order so far, that okay, first use nth term test. If it does not work, you see if your series is a p series. Again, it's not applicable all the time because you might have different kinds of series as well. So if it is not p series, then is it geometric series? So that's what we are going to talk about next. What kind of series is a geometric series? So I'll give first examples of the geometric series. Say you have summation 2 to the power n equals to 0 to infinity. So when you expand it, what do you get? 2 to the power 0 plus 2 to the power 1, 2 to the power 2, and so on. So it's 1 plus 2 square plus 2 cube, and so on. Of course, you can also write 1 plus 2 plus 4 plus 8. But when you're writing it like this, it's very easily recognizable that, okay, it's the powers of 2. All of the numbers are powers of 2. So any series of this kind in which each term is obtained from the previous term by multiplying with the same factor. So you have a common multiplier here. So the common multiplier here is 2. You're going to the next term by multiplying with 2. 2 times 2, 2 times 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and so on. So this kind of series is known as geometric series. You can have more example. Say you have 1 over 3 to the power n. Say n starts from this time 1 to infinity. So in this case, the first term is 1 over 3, then 1 over 9, then 1 over 27, and so on. So in this, you are every time multiplying with 1 over 3. So 1 over 3 is the common multiplier. So this series are known as geometric series, right? So in general, how does a geometric series look like? So there is a common multiplier r, which is raised to the power n. That's why its powers are varying, right? You see, it was 2 to the power n, it was 1 over 3 to the power n. So powers are varying. So it's r to the power n. And there could be some additional common multiple present there as well, which is multiplied with r to the power n. So this a is not raised to the power n, only r is raised to the power n. N is 0 to infinity. When you expand it, so it's a plus ar plus ar square, and so on. So a is just the multiple of all the terms. You can also pull it out. So it is 1 plus r square, and so on. So once you recognize that your series is a geometric series, so you can apply the geometric series test. Now, what exactly is a geometric series test? So it tells you that this series is convergent if and only if the magnitude of the multiplier, means the absolute value of r, is less than 1. So it's an if and only if situation. That means if the magnitude of multiplier is less than 1, then it's convergent. Otherwise, not convergent. Not convergent means divergent, right? So you can say if mod r is less than 1, then the series is convergent. And if mod r is greater than or equals to 1, then the series is divergent. So this is a test which is applicable to a particular kind of series, but it is capable of telling you both the things, whether convergent or divergent. So go back to these examples which we just did. So you see this one. If you compare it with the general type, so here a is 1 and r is 2, right? So there's nothing here, means it's 1 here. So multiplier is 2. So the magnitude of the multiplier is greater than 1. That makes this series divergent. But here, the magnitude of the multiplier is less than 1, so which makes it convergent. Now, why we are talking about magnitude? Because sometimes we can also have negative multipliers. So in order to take care of that, we have to use the absolute value sign. So you see, it's only the multiplier r which decides the convergence or divergence. A has nothing to do in deciding the convergence or divergence. But A has something to do with the sum of the series. See, I told you in the beginning that we are always trying to answer this question whether a given series is convergent or divergent. Now, if it is convergent, we know its infinite sum makes sense, it's well defined. So now, can we find that formula for the sum? So not in every case, but for geometric series, we do have that formula. So if the geometric series is convergent, then there is a formula for sum of the series. Then its sum is a over 1 minus r. So it's not like we cannot find the sum of the series for p series or more different kinds of series. There are more difficult or analytical ways to find their sums. But for geometric series, we do have a simple, straightforward formula which is applicable to all types of geometric series. So we are going to use this one. So this is often used as a hint as well. Like in questions, if you see that, okay, determine if the series is convergent or divergent. And if it is convergent, find its sum. So they don't tell you that your series is a geometric series or you have to use geometric series test. But when they ask you to find the sum, it will be a hint that, okay, since we only know the formula for the sum for a geometric series, so that means it is a geometric series. So you get a hint and you can use that to do your advantage and, of course, attempt that question. So here I'm going to give you more examples of geometric series which are not very straightforward. So here I have one example. Summation n is 0 to infinity 3 2 plus n times 2 1 minus 3n. So it doesn't straight away looks like a geometric series because there are powers of n, but you also have 2 plus n and 1 minus 3n. So you can do some algebraic manipulation here. Say you have 3 to the power 2 times 3 to the power n. 2 to the power 1 times 2 to the power minus 3n. So these are the rules of exponents that you can break down the powers and make the bases same. So this is 2 plus n, 1 minus 3n. Now I see these two, they are just constants. So 3 square is 9 times 2 is 18. And you have 3 to the power n, 2 to the power negative 3n. Now we can shift the negative exponent to the denominator. So this becomes 2 to the power 3n. And now further, you can rewrite it as 18, 3 over 8 to the power n. Because you can take a common power n outside and inside you're left with 3 over 2 to the power 3. And 2 to the power 3 is 8. N is 0 to infinity. So now it definitely looks like your series a r to the power n, where a is 18 and r is 3 over 8. So you can do that comparison, right? So once you have a and r, once you have recognized it's a geometric series, now you can use the test. So the test asks you to find absolute value of your multiplier, which is 3 over 8. Its magnitude is less than 1. 3 over 8 is less than 1. Thus, the given series is convergent, right? So you answered one question, this is convergent. But if the question further asks, okay, if it is convergent, can you find its sum? So here we do have a formula for finding sum of the series a over 1 minus r. Now a in this case is 18, r is 3 over 8. So that's 18 over 1 minus 3 over 8. When you simplify that, that's 5 over 8 and then 144 over 5. That's the sum of the series. That means if you expand this series, all of the terms add up to 144 over 5. It's an approximate sum always because you are never going to know the exact sum because the terms are infinite. You keep adding more terms. But the beauty of convergence is even if you're adding more terms, those terms in the end are so insignificant, they do not change the sum. So the sum kind of saturates at some point. So that's the value we are looking at, 144 over 5. So that's geometric series. We did some examples where I told you it could be convergent, divergent. These were a few examples and so we are into our list. We did 3 tests. What if your series is neither a P series and not a geometric series? It could be anything else as well. So we need more tests because not every series falls into those categories. So the next test we are going to talk about here is a ratio test. Now, as the name suggests, the ratio test is nothing but taking the ratio of two terms of the series. Because we are given only one series, we cannot take its ratio with another series. Here, it's an intrinsic test. All the information about the convergence of the series is present within the series itself. So it's like how the terms are interacting with each other. So ratio test tells you to take the ratio of n plus 1th term with nth term and find the limit. So suppose this is L. Now there are 3 possibilities here. If L is less than 1, that means if this limit exists and it turns out to be a number less than 1, it could be 0, it's fine, it should be less than 1. Many of the times students get confused, okay, it's becoming 0, should we compare with 0 or not? You should only compare with 1. If it is less than 1, then the series is convergent. The second possibility is if this limit is greater than 1 or this limit goes to infinity, right? So going to infinity means limit does not exist. That case is also covered in possibility number 2. If this happens, then your conclusion is the series is divergent. And the third possibility is if L is equals to 1, then what happens? Then we say the test fails or is inconclusive. So in this case, if test fails or inconclusive, that means again we have to rely on some other test, right? So you can use ratio test. If it works, it works. If it doesn't work, think about some other test. Now, what kind of questions you are going to use ratio test on? So it's clear from the name. Whenever you see a fractional form of expression, so where you are given ratio of two things, so there you can use it. But another important category where you can use ratio test is the general term containing factorials. It's the biggest hint because it's very difficult to otherwise deal with factorials using any other test, be it nth term test or any other. But ratio test is the answer whenever you have factorials. So you see it covers a vast majority of ANs, vast majority of series. The moment you see factorials as a function, use ratio test. So I'm going to give you an example for the same. So say we had, just give me a moment. Yeah. Summation n equals to 0 to infinity, 2n factorial divided by 5n plus 1. So in this case, your an is 2n factorial over 5n plus 1. Now the ratio test wants you to take the ratio of n plus 1th term with nth term. So for that, you have to first compute n plus 1th term. Now for computing n plus 1th term, you need to change n to n plus 1 in the entire expression of an. Be very careful with it because if you do it like this is wrong because n is multiplied with 2. So the whole thing, n plus 1, needs to be multiplied with 2, right? And factorial outside. Similarly, 5, n replaced with n plus 1, and then plus 1. So when you simplify this, so it's 2n plus 2 factorial, 5n plus 6. And now you will see why we use ratio test here, because it has the capability of dealing with factorial in a much easier way. So when you take this ratio, so an plus 1 over an, right? So I'm just writing the whole thing. And now you algebraically simplify this first, right? So simple rules of fractions, flip this over, goes into multiplication. And remember, you have to take limit n goes to infinity. But before taking limit n goes to infinity, we are doing some simplification here. We want to get rid of factorial before applying the limit because It's hard to process limit n goes to infinity for factorials, especially when they're coming in ratio. So that's how you simplify this. So you combine the factorial term with the factorial and rest of the terms, group them together. So not introducing any new terms, just moving them here and there, rearranging them so that we can simplify them. Now there is a rule for simplifying ratios of factorials. Whenever you have multiple factorials in the same expression, you always simplify, or I should say expand the bigger one. So out of 2n and 2n plus 2 factorial, this one is bigger, so I'm going to expand that one. So 2n plus 2, 2n plus 1. So that's how you expand factorial. 5 factorial is 5 times 4 times 3, right? So you keep decreasing the integers one by one and end up getting at 1. But here we are not going to do all the expansion till 1. We'll stop at 2n, because after 2n plus 2, there will be 2n plus 1, then there will be 2n. Stop there. So factorial, use a factorial. Why I stopped here? Because I already have 2n factorial in the denominator. So I'll be able to cancel that. And 5n plus 1 over 5n plus 6. So let me rewrite here what we are left with. Limit n goes to infinity, 2n plus 2, 2n plus 1, 5n plus, what was it? 1 over 5n plus 6. Now, if you simplify this part, 2n plus 2, 2n plus 1, so 5 plus 1 over n, 5 plus 6 over n, because that's how you solve limits at infinity. You can also use L'Hopital's rule for that part. So I just divided with n by taking out n common. So this is what I got. So these both go to 0 as n goes to infinity, and you're left with 2n plus 2, 2n plus 1, 5 over 5. 5 over 5 gets cancelled, equals to 1. And finally, you are just left with this expression. Now, if you want to multiply them, you can, but otherwise, straight away, you can see the answer is infinity, because it's a polynomial in n. There's nothing in the denominator. So this whole thing, because n is sitting there with a positive power. So if n goes to infinity, the whole thing goes to infinity, right? So this limit goes to infinity. So as per the conditions of ratio test, it falls into this category, condition number 2, that if L goes to infinity, then the series is divergent. So the conclusion is, given series is divergent, right? So that's an example of ratio test using factorials, and most of them need this much, I would say, effort, because of the presence of factorials. So you need to do a lot of simplification. But yeah, one thing for sure, 99% of the example, they are doable using ratio test whenever they have factorials. So that covers like a major chunk of problems, that the moment you see factorials, use ratio test. You can also use ratio test on a non-factorial example. So for say I show you this one maybe, but I'm not sure whether it will be applicable here or not. Like for this, we already know this is divergent. But suppose you did not use an nth term test and you directly went to ratio test. So let's try this one with ratio test as well. So an plus 1 over an. So an plus 1 is going to be 2n plus 1 over n plus 1 plus 2. An is 2n over n plus 2. When you take that ratio, yeah, so actually in this case, if you simplify this limit, it will turn out to be 1. So we can say the ratio test fails or inconclusive. So then you will remind yourself that, okay, ratio test is not giving me the answer. Maybe I need to try nth term test. So that's what happens. I'm just trying to give you examples of the patterns of the brain, which happens naturally when you do these kind of questions, that if you try some test, doesn't work, go back to your basics. Okay, use nth term test. So in this case, Ratio test didn't work, but nth term test worked for us. So yeah, there could be questions where more than one test is giving you the answer. So whatever clicks you is right. But yeah, if one doesn't work, then definitely you have to rely on the other. So that's an example of ratio test. And now we are going to do an example of a root tests. But before that, I'll just define what is root test and specifically what is nth root test. Now, nth root test is about raising the general term an to the power 1 over n and then computing limit n goes to infinity. Now, the good thing about root test and ratio test, like we always say they occur in pairs, ratio root, because the conditions, the decision-making conditions or the possibilities for both of them is exactly same. It's only the limit which differs. In ratio test, you take the ratio of n plus 1th term with nth term and then take limit n goes to infinity. In root test, you don't compute n plus 1th term. You only consider a nth term and raise it to the power 1 over n. That's the meaning of nth root. And apply the test. So if it is less than 1, then it is the series is convergent. If the limit is greater than 1 or limit goes to infinity, then this is divergent, means the series is divergent. And of course, if it is equals to 1, then we say test fails. So you see the conditions are exactly same as a ratio test. But what makes it different? Like, how do you know whether you have to use ratio test or root test? See, for ratio test, I told you the hint is, okay, factorials or fractions. For root test, I'm going to give you the hint that whenever an contains n in the exponent, right? So n or some function of n sitting in the power of an, then use root test. Because then if there's already a power n and you raise it to the power 1 over n, you get rid of the power, right? That's the goal. You want to get rid of the power. So to balance that, raise it to the power 1 over n. So that's a primary, I would say, hint for it. So I'll give you an example for the same. Say you have to test this series n 1 minus 3n over 4 to the power 2n equals to 0 to infinity. Now in this case, your an is n to the power 1 minus 3n over 4 to the power 2n. You can break it down like n to the power 1, n to the power minus 3n over 4 to the power n. Now, since the n is there in the power, so I plan to use root test. So when you raise the whole thing to power 1 over n, so wherever you have n power, that's going to balance with the power 1 over n. So it's, now this one does not contain power n. This is just 1. So it will be 1 over n. This will be minus 3 and this will be 2 because here you had power n, so that balanced with 1 over n. Here you had n, that balanced with 1 over n, but you left with the constant multiples 3 and 2. Here you did not have n, so that introduces an additional power 1 over n. Now if you take limit n goes to infinity, now this is a standard, there is a standard limit. There are some limits in calculus, we put them into the category of standard limits because they appear so frequently, and to find them or always working them out takes all the same steps. So we don't want to repeat these steps all the time. So what we do instead, we just remember their values because of their appearance so much frequently into the calculus. So this is one of those limits. So whenever you have limit n goes to infinity, n to the power 1 over n, it's 1. So that's 1. So this part is 1. And now you're left with 1 over 16 n cube, because n to the power minus 3, you will shift it to the denominator, n cube and 4 square is 16. So this whole thing goes to 0 because n in the denominator with a positive exponent, you take limit n goes to infinity, it goes to 0. 0 is less than 1. So it falls into this case. So hence this series is convergent by root test. So it's all about recognizing which test is applicable. I'm not giving you all sorts of example, but I'm just trying to give you one example for each test so that you just have an hierarchy of the test application in your head, right? So far we are at, okay, very first thing you need to use is nth term test. If it doesn't work, identify if your series is a P series. If it doesn't work, identify if your series is a geometric series. Otherwise, think about ratio test or root test, right? We do have more tests here. We do have comparison test as well. We have integral test as well, but I'm not going to do all of them today. So I'm going to talk about only one of the tests, one more test, so which is an alternating series test. And sometimes, although I suggest try this, but sometimes this is difficult. Like if you take an example of the question which we just did with the ratio test, here, before applying ratio test, if you would have tried nth term test, that means if you would have tried computing this limit n goes to infinity an, right? You want to apply the nth term divergence test. Then sometimes it's so difficult to solve this limit because of the presence of factorial. So you'd spend so much effort in solving that limit and you're not reaching somewhere. So it's better to quit applying nth term test and proceed with the ratio test, right? So it's not always workable because sometimes computing limit n goes to infinity an is a challenge. So in that case, we skip this one and go towards the next. But if it's easy, then definitely it's helpful if it works. So you have to have a lot of practice for developing these ideas in your head that, okay, if this happens, then what should I do? If this happens, then what should I do? So the next test we are going to talk about is alternating series test. For that, we need to understand what is an alternating series. Again, now this is a test which is specific, very specific to one kind of series, alternating series. And what's the recognition of alternating series? So this is how it looks like. So alternating series, if I give you example, is 1 minus 2 plus 3 minus 4 plus 5. So the terms are following some formula, but the signs of the term are alternatively plus and minus, right? The first term could be positive, the second term could be negative, or vice versa, but the terms are changing sign alternatively. If that is the kind of series you are given, it is an alternating series. And whenever you have alternating signs, so here we will always have this term present, negative 1 to the power n times something, right? So I should actually use a different notation here. So maybe let's call it un. So the whole of this is general term an, but an has like two parts, negative 1 to the power n and something else. Now this is sometimes an could also be negative to the 1 to the power n minus 1 or n plus 1. So that doesn't change anything. It still is alternating. So you could also have minus 1 to the power n minus 1. It is still alternating, right? But if you have minus 1 to the power 2n, then definitely this is not an alternating series. Why is that so? Because negative 1 to the power 2n. 2n is an even number. This is plus 1. So this will be all positive term series, not a negative or alternating series, right? So be very careful with those tricky questions. So that's the recognition. These three powers and some other function of n present, it's an alternating series. For example, if you have minus 1 to the power n over n, minus 1 to the power n plus 1 over 5 and factorial, something like that, right? So you have a function and you have negative 1 to the power n or negative 1 to the power n plus 1. So once you recognize it's an alternating series, then you use alternating series test for convergence, also known as Leibniz tests for convergence. Again, it's a convergence test. You can never imply divergence using this test. I'm not saying alternating series can never be divergent. It can be divergent, but this test does not qualifies to account for the divergence. This test only can prove convergence, never prove divergence. So what this test is. So this is your series.